Hello, this is Math 2270 coming to you from the College of DuPage for summer of 2020, and the topic of this lecture is Bernoulli. Lobachevsky was a great Russian mathematician in the 1800s. He also served as the chancellor while he was doing his mathematical research of a great Russian university. His quote is, "There is no branch of mathematics, however abstract, which may not someday be applied to the phenomenon of the real world." As far as I know, there was no particular motivation behind the development of the Bernoulli equation. The Bernoulli family was quite renowned for taking up hard challenges in mathematics and giving solutions for particular cases, and sometimes brilliant generalizations. In other words, they often solved problems for the challenge and the thrill, rather than for potential applications. That is what mathematicians do today. As for its derivation, Jacob Bernoulli must have probably just seen it as a natural extension of the then existing theory of differential equations, and thus worked on solving it. Having said that, though, modern physics does indeed use Bernoulli differential equations for modeling the dynamics behind certain electrical circuits, known as Bernoulli memristors. I don't know much about this, but if you're curious, there's a paper that I will reference briefly. It's also used in optimal control theory. I know a little bit more about that. The Bernoulli family was an extensive family. This is Jacob Bernoulli. Notice that it is spelled differently. But the Bernoullis that you see highlighted here in bold-faced are all in the Mathematics Hall of Fame. They were an extremely brilliant family, and they were also dysfunctional. In particular, Daniel Bernoulli, in the middle here, this Daniel, was responsible for the pressure equation that is one of the main reasons that airplanes can fly. And here's the abstract, and you can see that these Czech Republic electrical engineers wrote a research paper about this. So what is the Bernoulli's equation? This is what it looks like. Now you might say, hey, it looks a lot like what we've just been talking about, solving linear first-order differential equations, except we have this y to the n. That was the generalization. Now if n was equal to 0, it would just be the linear equations that we know how to solve. If n equal 1, you could move the y to the other side and it could be again linear. But if it is not equal to 1, and it can even be a fraction, then we make this substitution. U is equal to y minus 1. This was Bernoulli's idea. And what will happen is if u equals y raised to the 1 minus n, you have to figure out what u prime is, and that is going to be 1 minus n, y to the minus n, times y prime. So this is an important part of the substitution. We then can solve the linear equation and reverse the substitution. The joke is, that I'm going to make, is that mathematicians, when they're undergraduates, what they do is they are learning like how to extinguish a campfire. So they go to the river, fill a bucket, come back, and dump the water onto the campfire, and it is extinguished right there on the beach of the river. Graduate mathematics and research mathematics, what you do is you have a fire on top of a mountain, and the stream is at the bottom. So you go to the stream, fill the bucket with water, then you have to climb the mountain without spilling the water, and the idea is then you could extinguish the campfire. Now, the mathematician, though, would stop right at the campfire's edge and put the bucket down and say, the rest of this is undergraduate mathematics. I am through. And you see, once we reach this part, Bernoulli would say he is through. I've got to tell you, in the real world, where I was an applied mathematician, you have to finish the job. You as engineers will have to finish the job. Okay, let's look at some of the details, though. And oops, I need to switch V with the U that I had on the previous slide. That's one of the reasons I will never write a book. You have to be too careful about those things. But anyway, okay, so we started out with the differential equation you saw on the previous page. You divide all the way through by n, by y to the n. And so we get it on this side, and now we have just a function of x on this side. Now here's where I switch, and instead of calling it u, I call it v. But then v prime is what I said it was on the previous page. And we substitute this into this equation carefully, and you should verify these details, and you get this, which is almost the form we need. The only thing that's different is this factor, and you have to deal with that. And so you multiply all the way through by that, and then you'll be good to go. There's nothing like doing an example, so here's an example. You see you got y squared over here, so you solve the following IVP and find the interval validity for this. And notice that x is bigger than 0. You know what to do. Let's see how you did. All right, so what we do is we move the y squared to the other side like this. This is the substitution that we use, and that becomes this with taking the derivative. I substitute this into my original equation and I get this. Now it is worth noting this is not in the form we need exactly because of that -1, but that's easily fixed and we fix it here. So now this is now a problem, and realize that now this is going to be plus -4 over x. You see these details really do matter a lot. But now you can solve this with an integrating factor, and you find the integrating factor is x to the -4. You should go through and verify these details. But there's my integrating factor, so I multiply all the way through by it, check that this is an exact differential, and then what I'm going to be doing is I am going to be integrating this expression after I do this. Again, this is stuff we've studied before. This is stuff that you will have to do. Bernoulli would have quit by now. So you integrate, you get this, and then you find out that v is this. But we really wanted to know about y. So we will put what y was in terms of v, and we have this expression. We can plug in our initial condition and find out that c is this. Some of my students would say this is an ugly number, but I tell them there are no ugly numbers, just like there are no ugly babies. So this is the c, and that means that y is equal to this after some simplification. Now, x was greater than 0, so we don't have to worry about the singularity at 0. But we do have to make sure that this isn't equal to 0, so we work through and we find out that would be equal to 0 when x is 2 e to the -1 over 16. Now, so we have to avoid those points. That gives rise to two possible intervals of validity, this one, and the one we're going to pick is this, so this is the interval of validity. So we have solved the problem. I'm about finished here, but I am going to pose this problem. You should work on it. And we'll pick this up with the solution in the second half of this lecture. You know what to do. See you in 9.3.